Of amazing stories, and let's before kickstarting with the theme of professionalization today, let's start by looking back at the assignment shortly after, then followed shortly by the syllabus, and then go to the theme. First, a couple of prejudices from last week's assignment. And the first two are you're getting better at this really. I see less prejudice and I see better formulations. So thank you for that. It's becoming increasingly harder to find actual prejudices in your texts. But there are a couple, and here are two which are rather difficult to spot. First one, purification of mathematics implied that the applications were no longer important to the mathematician. And this is a misconception, really. This is not even a prejudice, this is a misconception. To us today, the pure mathematicians may think, at least I know there are pure mathematicians who really think that the applications are less important. This does not apply to the 19th century mathematicians, neither does it to the early 20th century mathematicians. All of them, well, with the notable exception that proves the rule, all of them were convinced that applications were important. The notion of application started shifting there. Yeah? So calculus became an application of analysis. And mechanics became, in the early 20th century, became an application of mechanics, became an application of calculus, or of analytics, whatever, yeah? So the notion of application starts shifting. If you have a look at the general theory of relativity or quantum mechanics, that looks like mathematics. To the mathematicians, that was applied mathematics. Yes, so the notion starts shifting by the pure mathematicians. But it's not only the pure mathematicians that we're talking about here. I hope at least that becomes clear from reading the syllabus and from listening to my stories. There are different mathematical worlds that do communicate among each other, but sometimes simply don't understand each other, or come together but have different conceptions of what mathematics should be about. The mathematical world of the mathematical world of the technical education is having difficulty understanding the mathematical world of the pure mathematicians at the universities by the end of the 19th century. So these worlds drift apart, come together again, and weaver in any direction. Different conceptions of what mathematics is about. That's the whole point. There are mathematics students here, there are business analytics students here. You have different conceptions of what mathematics is about as well. And there's nothing wrong with both your conceptions. Or perhaps there are more than two, yeah, floating around. Both are valid. But still. So please don't think that the applications were no longer important, the applications remained important. You see, certainly people like Vrije, but also Klein, they are heavily involved in applied mathematics just as well. The second one, I love that one, because here it's really becoming hard to spot the difficulty. As time went on, the use of limits became more popular, as well as the use of definitions that are useful for proofs, and the idea that proofs should be watertight, which is absolutely true. Absolutely true. There's nothing wrong with this sentence. But, one but. Yeah? Proofs should be watertight. That there's not a prejudice here, there is a value behind that, an important value behind that, behind these words. When do you find a proof is watertight? Newton wasn't doing his Principia, writing his Principia idea, oh, I don't mind about the proofs, I'll just drop something down and it's not important whether it's correct. No. He was convinced that he was proving something. But he had his own norms and values about what a good proof is. And this shifts in the early 19th century. This shifts. Yeah? Well, when Benjamin Franklin does moral algebra, he's not interested in proof. Proof is not that's not relevant to him. He has this idea about weighing various ideas about a certain subject, and if he thinks that, if one outweighs the others, he knows which decision to make. It's an algorithmic view of what mathematics is about. There's nothing wrong with an algorithmic view of what mathematics is about. It just bears little or bears much less importance to proof. It still has, well, at least the claim of mathematical respectability, the claim of mathematical reality, the claim of mathematical certainty to it. Mathematical certainty can be a very important value and does not necessarily have to go accompanied by proof. And if it does go accompanied by proof, then you still can have different values on what that proof should be. Should it be according to, should it be based on set theory? Should it be based on whatever? Yeah, you can choose differently. Newton had another set of norms and values in that sense than Cauchy a century and a half later. So is that progress? Well, in a sense it is. I like to think that Cauchy's is better than Newton's, but in its own right, Newton thought and was convinced and had good reasons to believe so that his proofs were watertight. So in the word watertight are very fundamental and very important values hidden. Please bear that in mind. A proof can be called beautiful. Yeah? And some are. I truly think that they are, at least. But there are values behind that as well. I can tell you there are people who will not spot the beauty in a good proof. That's telling. Then two who I really want to discuss. For some reason, a lot of you talked about cars. In the difference between calculus and analysis, cars were far outnumbered by any other metaphor. Use of metaphor can be advantageous. I would encourage using metaphor even, but be careful. If you use metaphor, be fair and immediately spot the value behind the metaphor. There's always a value behind a metaphor. If you present a metaphor as like this, if analysis is about building the car, then calculus is about driving it, then please realize that you could also, with the same ease, say, if analysis is about designing a car on paper, then calculus is about building it, yeah? And which makes it less favorable to analysis. This looks very favorable to analysis. Yeah, every metaphor can be used both in the direction that it is intended, and it can be used in the opposite direction. Beware of metaphors and spot the values behind those. Metaphors are an important tool, and they are sometimes illuminating, mostly illuminating for the values that hide behind the ideas. And here, indeed, building a car is suggested to be much more important than just being able to drive it. This is exactly the paternalistic kind of metaphor that you'd expect from a mathematician. Is that wrong? No, it's not wrong. Just be aware of it. You can, and the typical engineer would say, well, the mathematician understands the concept of the car, and I can actually build one, which is much more. Which one do you prefer? And so is the second one. Who would trust a car mechanic that has no idea about how a car functions? Yeah? There is no car mechanic. This is a very nice metaphor as well, but very, far-fetched even. There is no car mechanic who has no idea about how a car functions. The question here, or the matter raised here, actually, is not about trusting that mechanic, because unless one of you is actually a car mechanic, you trust the car mechanic more than yourself when you go handling the car. It's more a matter of what is the level, what do you want him to understand? Do you want him to understand combustion? Do you want him to understand the whole concept of force and inertia? And what do you want him to understand? You can have the car mechanic understand various things about this car, but what he has to do is bloody repair the thing and get it running again. That's what he has to do. And usually he succeeds. And I have no idea about his level of competence. I have no idea whatsoever. So do I put my trust in? Yeah, I trust him in that matter that I know he does a better job than I would, which is a good thing. So here there's a value hiding behind the metaphor as well, and the value hides in that idea about how it functions. What kind of level of competence do you want your car mechanic to have? Do you? Yeah, please.
So a better question would be something like, does it matter if a car mechanic knows how a car functions if he knows how to fix it?
Well, if you are a car owner and you want your car fixed, yes. If you happen to be teaching a car mechanics institute where you are where you're educating car mechanics, you bloody have to think about what level of competence do you want your students to acquire. Yeah, then there's a completely different question at hand. So it's easy to discard things like the car mechanic, but it's good to think or to realize that there are values behind these kind of remarks. And by spotting the values, by spotting the prejudices, you can at least decide whether you agree or not, whether you want to make it into a coffee table joke or do something serious with it. That's the point. The last remark, these kind of words, better proofs, more efficient, all these words, better, more efficient, it hides values. If you have a better proof, if one proof is better than the other, then it is better according to certain values, according to certain rules, according to certain things that you prefer over others. Is there a reason why you prefer them? Well, there could be a good reason. Think about it. But it might be, just, preference. There's nothing wrong with prejudice, there's nothing wrong with preference, but historically you can become aware of it, and that's what I try to convey here. More efficient, same thing, Something's more efficient according to certain specifications. Or perhaps you just call it more efficient as a way of trying to convince someone this is much more efficient. Don't bother this. You can try in a rhetorical fashion. You can use the phrase yes, and then it's empty. All of us want. That's usually the goal. That's what our rector keeps telling us every year again during our annual education day. We want top education, we want brilliant minds, we want genuine involvement from the students. And well, who could disagree? Who could disagree? Of course you want top education, you want the best teachers, you want it all. But as soon as we go into detail, what do we mean by that top education? What? As soon as then the people start fighting. We don't agree. We simply don't agree. Some of us think, that it's important to have students educated in analysis. Others think, well, calculus will do just fine, and yet others think, well, why analysis or calculus at all? Well, let's do something completely different. Yeah? And all of them have good reasons. All of them have, really, they really do. And when you start listening to each other, you find out that these different values behind what good education actually means, what trying to involve students actually could entail and could yield. At that moment you discover that you are really, well, not agreeing on what the goals of education are. Or you may find out that people are more prejudiced than you hoped for. All of us are. So, when you write down something like better proofs, more efficient, be careful, reflect for a moment, at least within this course. Yeah? Reflect for a moment, but preferably in the rest of your future days. Reflect for a moment and think, according to what? And do I agree with that scale? Do I? Okay, now, the next one. Oh yeah, there were two questions that Vincent pointed out to me that were not particularly well made. Many of you had great grades, so there's no complaint there, but Vincent warned me to pay attention to the nation-state question in particular and the calculus question as well. The nation-state. The question is to give ways, a plural, yes? Please, if there is a plural, try to mention at least 2 ways, not just one, that helps. Yeah? Just reading helps. The example of education was mentioned by almost everyone, so that's quite okay. Although often without a good example, and mind you, education can be interpreted in I think 3 or 4 ways as described in the syllabus. Anyway, so you can talk about production of textbooks, then there are several names mentioned. You can talk about textbooks in elementary algebra, geometry, whatever. You can talk about aiding in the formation of citizens by teaching in this new didactics. That's slightly different. Of course, you convey that idea through textbooks, but you also convey it by teaching classes. You can also use the example of technical education, and there are names and there are examples of all 3 of these subjects in the syllabus that you can use. There are other examples that you may use just as well, but these are just 3 lines of thought that fit education. But then the second example, that was mostly absent. You could take 2 examples from education, of course, that's quite feasible. But the second example could also be constructed around the introduction of the metric system, which was not only happening in education. Of course, education helped. If you force everyone to go through elementary education, then you have the opportunity to teach them all the metric system, and then you're done. But the people who were not going through the elementary school system anymore, or either because they were too old, or because they simply missed out on education. There was no formality there was no obligation of attending school until the 1854 law. So you missed out on a number of people. For those, you needed other things. And there is this nice example in the syllabus from a Dutch picture that was handed out on carnivals and such, showing the merits of the metric system simply by showing that it was very Dutch and thereby deserved attention and deserved it. There are examples of books which were handed out to people in the street, introducing the metric system as the way of measuring, the exact way of measuring, the best way of measuring. Why? Because it was founded on creation. We have measured the globe, We have measured the globe and we've divided it into 40,000 similar pieces, and that's the basis of our new system. And we only need that measure. From that measure we can derive the measure for area, for volume, for whatever we want. Yeah, so, yeah.
Is that the way they sold it to the public?
Yeah, that's one of the ways, yeah. By telling them that it was Dutch, by telling them that it was founded on creation, yeah, that it was, what else? That it was not difficult. That was the most important reason, really, because inherently it was difficult. The metric system is inherently difficult, more difficult than the former system. Was that clear from the syllabus at all? Hardly. A little bit. Was that clear to you? Yeah, just no, you. Yeah, yeah.
It was quite clear.
It was quite clear. Good. Okay. And was it clear to you? Yeah, almost. The idea of the old systems. Let me briefly explain that. Just the idea of the old system is very, very simple. You measure by counting. So an area. We would say an area is square meters or acres or whatever. Yeah, that's how we measure an area. To the 18th century people, an area could be measured in a time unit. So many mornings, 3 mornings, was a very common use to denote an area, and that signified that it took you, as a farmer, 3 mornings to actually plow the area. Which is important to know as a farmer. But it says 2 things. It says something about how large your area is. It also tells you something about the ground itself. Are there a lot of stones? Do you have to step off your plow every minute because you have to remove another stone? Or is it heavy clay, which goes very, very slowly? It tells you 2 things. Yeah? But it's easier. In that sense that if I add another morning to my land, I know how much time it will take me to plow it. And it has the advantage of being linear, where square meters are notoriously, well, linear in a sense. If I try to work them out to another sense, another type of square area, there is a linear connection. But if I go from square meters to square decimeters, I have to keep in mind that I don't only divide up the length, but also the breadth of the area. So I get instead of a 10-fold multiplication, I get a 100-fold multiplication factor. Which is why in every elementary school today, even, you'll find teachers who find it difficult to explain to their pupils what this metric system is about, how to convey one measure into another, how to go from square meters to square centimeters, or from and then not using the same quadratic conversion factor if you go from square meters to acres. Yeah, that's funny, right? Yeah. It is inherently difficult in that way. It presupposes the metric system presupposes some elementary geometry. And the old systems are simply like if you're playing with marbles on the school's ground. They are completely linear, completely simple, and non-decimal, which is not relevant if you don't use Arabic numbers to note them down. So, yes, there is the metric system is, in a sense, difficult. And in the early 19th century, I would, with slightly exaggerating, I would say there were only a few people actually benefiting from the metric system as such, and that were the astronomers who were doing measurements and could now more easily share among each other, because all of us were now using the same measurements. There were the surveyors who were doing measurements, and there were the governments who were interested in unifying their country and trying to stop the madness of having to convey measures when you traveled from Amsterdam to Leiden or whatever other direction. Yes, please.
Wasn't surveying not disappearing at that time as a job during the
it was.
system was introduced?
Disappearing is no. It was disappearing from mathematics. As a job, it wasn't disappearing.
As a job on itself.
Yeah, it became a job on itself. It became a mathematical practice that was no longer considered to be mathematical by the mathematicians, by the pure mathematicians. Yeah. So surveying still takes place. We still have surveyors running around measuring stuff and trying to map where the building is going to come. Okay. So use one of these other examples to illustrate the reasons or the ways in which mathematicians try to be beneficial to the nation state. And the metric system is an example. Mathematicians, for some reason, or no, probably because of self-interest, a lot of mathematicians were standing behind the metric system. It made them sell more books. They could produce a new book. Hey, I've written a new book and it uses the metric system, buy it. Yeah, that works. But it also helped them to introduce, it helped them being introduced into upper social class circles. Yeah, we will help you. Yeah, we will help you conveying that, bringing that metric system to the people. For most people, it was completely irrelevant how many acres of ground they had. If you were plowing it, you wanted to know how many mornings it was. Yeah. Farmers involved in growing fruit crops were interested in how many trees their land had. So their area was simply denoted in trees, or how many volumes they would get, so many caskets. That was their way of denoting the area of their land, and not the number of square meters. There's no reason to know your square meters unless you are a government who wants to unify a country, who wants to raise taxes on the basis of land ownership, that kind of things. Okay. So, the second one, calculus. Calculus education was one of the driving forces behind purification. That's at least as it is depicted in the syllabus. The emergence of pure mathematics was not self-evident. I really want to stress that once more, because that was, according to Vincent, insufficiently clear from many of your answers. Yeah? Mathematicians disagreed on what was a good proof, what was watertight. So the question by Abel to Gauchy, is this an exception to your theorem, is a genuine question. It's not politeness. It's a genuine question. Is this an exception? Question mark. Yeah? You can, or do I understand it wrong? What's going on here? I don't get it. Which is a powerful reason to try to be more precise. And so the example of Gauchy and Abel is telling, but the continued use of infinitesimals all across the globe, and I have here a second, Schrödinger's Analysis, I'll hand it round. It's a 2-volume analysis book, and it still uses 80-70, it still uses infinitesimals, as if that's the way to go about. It's not interesting to do it entirely on limit-based. Riemann and Weierstrass, in the meantime, were doing it completely limit-based, absolutics all around. So yes, you can, but you don't necessarily have to. Okay, one of the most in Bourbon, France, for example, Gauchy was not even used anymore. He went along with his king, who was not from the Bourbon family, but from that other French family. And in Germany, Martin Ohm called it überflüssig kompliziert. So, you can make it more difficult if you like, but that can be the reaction to. That Gauchy became our hero and our standard way of doing analysis. There's good reasons for that. There's very good reasons. At least I hope you agree. And if you don't, I hope you have good reasons not to agree. Yeah? But there are, yeah, and as a business analytics student, I would say, I don't care. There is no reason to be so precise. The calculus works for me. I can follow the rules and it works. So doing the calculations works fine. That's about calculus. Then, the reflection question. Analysis versus calculus. Many of you, well, many solutions, many views were described. Many views also very relevant, very good, very well described. What is relevant here, or what I show here is just an example that you could have picked, and I don't think I've seen it picked, not exactly like this anyway, but yeah, this is one way you could have approached it, historically. By the way, I like the idea very much to take a present day example, but please be precise and do elaborate on your example. Who thinks that way? Can you name someone, or can you at least name a school where it's used, or an educational system where it's used in that way? That helps. Be precise, be elaborate. Analysis versus calculus can be viewed from the view that calculus was developed first. It was sometimes called analysis because it was recognized that something new was going on. Both Leibniz and Newton and de L'Hopital and Euler all recognized they were doing something new. They were no longer building mathematics like Euclid did, from the ground up, constructing every step and thereby building mathematical objects. No, they were deconstructing it. They were presupposing that they had a solution and then followed it down until they had the essentials of that solution that they didn't know yet. They were doing it the other way around, deconstructing, and they call that analysis. And you can find several examples. You can name Newton, you can name Leibniz, you can name de L'Hopital, you can name Euler, who even named his book Analysis Infinitorum. Yes, so yeah, he used a specific word. So did L'Hopital, by the way. Leibniz and Newton, I would be inconclusive, but they probably used the word somewhere, but not that prominently as de L'Hopital and Euler did. So yeah, from a historical point of view, there was little difference between the two then really. Analysis calculus was the method of calculus, perhaps you could say. It was the way that they went about, a new way of doing it. Whereas if you look at Gauchy, their analysis is a different meaning, is popping up in a different meaning of the word. To him, to Gauchy, it really is a subject which is important because it explains calculus. So it's a completely different subject. His book are, well, in the book title, the word analysis means something different than the word analysis in the book title of Euler. To him, it's really a subject, a part of mathematics that is important because it explains, with help of the limit concept, clearly defined, what are the limitations and what are the possibilities of calculus. And he thinks this subject is important because because calculus was important, and he wanted to have clear and proper understanding of the subject, not only for him, but also for his students. And clear and proper here does not mean clear and proper ways of how to use it, how to go about, how to organize, how to do your calculations so that you find that area, or so that you can calculate that tangent. No, it's about understanding why this works and what requirements you have to bestow on your functions before it actually does work. So So he goes a little deep. He, of course, is confronted with different kinds of functions. Yeah, Fourier's functions, Fourier's and infinite series defining functions, are new in that world. To Newton, a function was simply something that he would, a path of a bullet or the path of a planet. They are pretty continuous, you can imagine, or at least you hope so. Yeah. So, to him, functions were, as an object, were less relevant. To Cauchy, who was trying to abstract, that was slightly different. He wanted to be more precise, and with help of people like Abel, he formulates proofs. He tries to be more precise. Okay, now about the values behind these, because that seems to be the tricky one. And since hardly anyone did these values, who could have a go at the values behind these two views? Anyone? What are the values behind? No, not much difference between calculus and analysis as a different subject, bringing the foundations to calculus. What could be a value for, say, Newton or Leibniz?
That applications are the essence.
Applications are the essence of that could be a value, yeah. Get that? Does that make sense as a value to you? Yeah. Could there be another one? Could you name another one? There are more examples that you can. Yeah. So you could, for example, look at the level of proofs. Yeah. So to him, to Newton, it's applications that matter. Yes. I think you can clearly explain that that's a value behind his view. But you could also say, explaining or trying to come to grips with creation, which is a very strong incentive for doing mathematics. Yeah, he's trying to get to it, and the good Lord won't deceive me if I do my calculations properly. Yeah, there is a value there as well, and there are others to be thought of. Yes.
Which of the two opinions, I guess, are from that value then? Is that Newton? Is that?
That's Newton's. Yes. Yeah. And what would you think that Cauchy's value would be?
I mean, that's what I was wondering about, because I don't know the other side of that.
Okay.
I wouldn't say that.
Perhaps your neighbor has some clue.
We argue with Cauchy.
Sorry?
Well, we didn't use Cauchy in this question.
No, you didn't. But probably. But what could be a value behind Cauchy's view on the difference between calculus and analysis? What could be a value there?
Maybe he just wants to understand mathematics for the sake of mathematics.
Mathematics for the sake of mathematics. That could be, for example, mathematics for the sake of mathematics. Which is not entirely true, I would claim, with Cauchy, because he still thinks that these applications are important. He teaches at the École Polytechnique, right? But mathematics for the sake of mathematics is a very important value that rises from the early 19th century onwards and then becomes, more or less standard in academic mathematics by the half of the 20th century. But only then it's becoming standard. So these kind of values we are looking for. Elaborate just a little on how these values connect to this view. So don't take it for granted that everybody will understand.
Do you have another example of a value for Cauchy?
If you would go into detail and see it, so you could go into detail about the proofs that he's delivering. You could say, well, what he values is the logic and the use of definitions that are, how do I phrase that? Use of definitions that are actually usable in your proofs, that make your, so he redefines what watertight means by demanding that the definitions are actually used in the proofs, which is slightly different. To Newton, he knew what he was talking about, like Euclid. They knew what they were talking about. They had this conception. And to Gauchy, that no longer is self-evident. He wants to get deeper in there. And that's a continuous thread in 19th century and early 20th century mathematics in the academia. We want to understand better what this is about. And you may, well, at least we know today, there is an end to that. You can't delve much deeper until you hit the ground somewhere. And if you don't, then your whole body of mathematics is just a flirt. So, today we kind of take it for granted that you have to define something and take it at face value. To Gauchy, that still was not.
So you question everything more.
Yeah. And questioning is a value in itself, you could say. Yeah. Okay. Then the syllabus. I hope you did have a proper look at the examples, the pictures that do pop up so now and then in the syllabus. All of these examples are examples that should make sense after reading the chapter. And if they don't, then they are simply bad examples and will be out in the next version, but I do suppose most of them are very relevant. One of the things that I do want to point out for the chapter that you prepared today is the introduction of history of mathematics. When I reread it just the other day, I noticed that it is suggested that history of mathematics came to life in the late 19th century. Well, that's not entirely true. There are histories of mathematics also in the 18th century, but as a profession and stimulating the profession, that's end of the 19th century. So Klein as presenting himself as a historian of mathematics, that's late 19th century. Earlier histories of mathematics are loosely written, and certainly not with the intention, and that makes the comparison quite good, really. Certainly not with the intention to state that pure mathematics is the essence of mathematics. So if you take an 18th century mathematics textbook, history of mathematics textbook, then it will be much more freely written. There's no mention of the three fundamental problems of Greek geometry, for example. It's not mentioned. And there are no foundational problems in the calculus, for example, because they are not recognized. Yeah? So you really see a huge difference between these textbooks. Any questions about the text? It was entirely clear. Or it was completely left unread. No? Okay. Then now, for today, the theme is professionalization, and the standard view is pure mathematics is on the rise. Finally, we get paid for mathematical research. That's the standard view of the second half of the 19th century. And what I try to describe in the syllabus, and what I will be conveying to you here, although I will pay considerable attention to what pure mathematics is going to look like in the second half of the 19th century, what it leaves out is that there are a number of new mathematical practices rising and becoming very important that are left out that way. It's not pure mathematics alone. It's mathematics education becomes a practice of its own, and is a mathematical practice in itself. Statistics, but also technology. These are becoming mathematical practices which are not paying lip service to that pure mathematics image that is, or not necessarily paying lip homage to those pure mathematical ideas that are abound in academics. Yes, pure mathematics is on the rise. Yes, people do get paid not just for doing, not just for their teaching, but also for their research. But that's not the only thing happening in the mathematical practices of the late 19th century. And in particular, education, I think, is a very, very, very important part because it legitimizes the existence of academic mathematics. Without mathematics education coming up in the early 19th century, there would have been no reason for mathematics faculties to grow into, to blossom into the field of mathematics that we know today and we take for granted today. Yes, please.
Is that split, is that a consequence of the rise of professionalism and pure mathematics?
Yeah, or vice versa.
Are they intertwined?
Yeah, they're definitely intertwined. I don't dare say whether one is the consequence of the other or vice versa, but they're definitely intertwined. With more education, you do get more mathematics teachers that have to be educated. But yeah, still, why becoming more and more pure? That was a concept of professionalization that will be discussed at length. Yeah, professionalization, that's the theme, and we continue after the break. Let's